So we talked about this one in class, but this is from theorem 5.10, which tells us which of the fundamental subspaces are perpendicular to one another. So this one is true. This one is also true because the magnitude of a vector v is equal to the square root of its dot product with itself. And so if v dot v is 1, then the square root of v dot v is also 1. The dimension of the row space equals the rank, then it's invertible. So this is false because the row space is the rank. The dimension of the row space is the rank. So it's always the rank. Okay. Every orthonormal set of vectors is linearly independent. This is true. That's the nice thing about having an orthonormal set. If Q is an orthogonal matrix, then Q is invertible. This is true because Q inverse equals Q transpose. Next, two eigenvectors corresponding to the same eigenvalue must be linearly independent. This is false.
Not a chance.
What it means to be an eigenvector is AV equals lambda V. So we could have a scalar multiple.
When is that one? That's tomorrow. And as soon as that's over, then I'll...
So if we had K times V is also an eigenvector. In R3, if two lines are not parallel, they must intersect at a point, so that's false. All right. In R3, the span of two linearly independent vectors is always a plane through the origin. This is true, and I want to emphasize this idea of being two linearly independent vectors is going to make a plane. So the span of two linearly independent vectors will be a v1 plus b v2, where a and b are real numbers. This will always go through the origin because when a and b are both 0, that makes the 0 vector. Every system of linear equations has a solution. That's false. We've seen systems of linear equations with no solution. If a set of vectors has the property that no two vectors in the set are scalar multiples of one another, then the set is linearly independent. That's false. So you could have a set where, two of the vectors add to make the other one. So it's not just about being linearly independent, or it's not just about being not scalar multiples. For any matrices, both A transpose and A transpose A and A transpose are defined. That's true. If you look at the dimensions, it's going to work out. If A is an m by n matrix, then the null space of A is a subspace. That is true. So the null space is all the vectors that map to 0. In other words, AV equals 0. So all of those vectors V that map to 0 is the null space, and it is a subspace of Rn. The transformation defined by T of x equals negative x is a linear transformation. That is true. So what does this transformation do? So it takes 1, 0 to negative 1, 0. So it multiplies it by negative 1. And it takes 0, 1 and maps it to 0, negative 1. And so the matrix for this transformation is -1, 0, 0, -1. So since it's a matrix transformation, it's a linear transformation. So we have a theorem about that. Let W denote that plane. Calculate the projection of that vector onto the plane W. So what I need to do first of all is I need to find an orthogonal basis of the plane. So let's start by parameterizing this plane. So if I have, so I can let y equal s and z equal t. So I'm going to get 2x is equal to 3s plus t, or minus t. And so x is equal to 3/2 s minus 1/2 t. And then y is equal to s and z is equal to t. So our parameterization of this plane is going to be that w is equal to the span of the vectors 3/2, 1, 0, and minus 1/2, 0, 1. And so if we want to, we can multiply those guys by 2, and we can get rid of those fractions. Okay, so there are the two vectors, and so if I dot product them with one another, I can see that they are not orthogonal to one another. So I do need to straighten those out and get a orthogonal basis to get started. So to make an orthogonal basis, I want to call this guy x1 and I'll call this guy x2. And so I'll start by letting v1 equal x1. So that's 3, 2, 0. And then v2 will be x2 minus v1 x2 over v1 dot v1 v1. So x2 is minus 1, 0, 2 minus, and then when I do v1 dot x2, I'm going to get negative 3 plus 0 plus 0. And then v1 dot v1 is going to be 9 plus 4 plus 0. And then v1 is 3, 2, 0. Okay, so you would just do that subtraction and you would get a vector that is perpendicular to v1. So I'll have minus 1 plus 9/13. So negative 13/13 plus 9/13 is going to be negative 4/13. And then we'll have 0 plus 6/13. And then we'll have 2 plus 0. So this is just 2. And so that is my other vector. And so since it's not, it doesn't matter the length of that vector, I can go ahead and scale that by 13 and just make my v2 be negative 4, 6, and 26. And so let's just double check that that is actually orthogonal to this vector here. And so if I multiply them together, if I dot product them together, I'll get negative 12 plus 12 plus 0. So they are orthogonal to one another and within the span, and they're both lying within W. Okay, so I want to do the projection of that guy onto this plane. So the projection onto W of the vector 2, 1, minus 7 is going to be equal to, I need to do the part of the vector 2, 1, 7 that is parallel to V1. So I'll do 2, 1, 7 dot V1 over V1 dot V1, and then in the direction of V1, plus, then I'll do 2, 1, 7 dot V2, and then over V2 dot V2 in the direction of V2. And so that is what I need to compute now. Okay, so if I do 217 dot V1, that's going to give me 6 plus 2. So that's 8 over, and then v1 dot v1 is going to be 9 plus 4. And then that's going to be in the direction of v1, which is 3, 2, 0. And then I'm going to do plus. If I do 217.v2, I'm going to have negative 8 plus 6, and then 7 plus 26. I don't know, 7 times 26. Over v2.v2. So do that dot itself, and then in the direction of v2. So, so you'll get 16 plus 36 plus 26 squared. So then you are going to add that all up, and that's going to give you your final answer. Okay, what does it mean for lambda to be an eigenvalue of a square matrix A? So it means that there exists a vector V such that AV equals lambda V. And then suppose that is a reflection across the line through the origin of R. What are the eigenvalues of A? So if I have a line through the origin, so if this is my line, and so this is some line y equals mx plus b, right? What are the eigenvalues of A? And so I can think about a vector. If it's a reflection, then I would have a vector, if the vector is 1m, so this vector, 1 comma m, is in the direction of that line, and so that's going to be an eigenvector. And so in that direction, all the points are going to be unchanged. So the vector, for the eigenvalue lambda equals 1, the eigenvector is going to be, maybe I can just write it this way. The eigenspace of the eigenvector 1 is going to be the span of the vector 1 comma m, because in the direction of that line, all points are fixed. Now, if I'm in the direction that is perpendicular to that, so that would be, so if it's perpendicular to 1 comma m, then that would be, let's think about how this needs to work. So it's going to be negative m comma 1. So this is going to be the vector negative m1. So if we go in that direction, then it's going to flip the point. So it's going to be lambda equals minus 1, because it's going to change that vector to the negative of that vector. And the eigenspace associated with negative 1 is the span of negative m comma 1. So you just have to think about what happens geometrically to these vectors. And so the vectors that are going to be fixed are going to be the vectors that lie along this line of reflection. And the vectors that are going to be changed by taking the negative of that vector are going to be the vectors that are perpendicular to that line. Okay, complete the following theorem. A is invertible, and then A times A inverse equals IN. And then the rank of A is n. The determinant of A is non-zero. The columns of A form a basis of Rn. The rows of A form a basis of Rn. And the null space of A equals 0. Let W equal the span of those two vectors. Find a basis for W perp. Okay, so one thing we could think about is what will be the dimension of W perp. So we are in, so these are 5-dimensional vectors. So this is a subspace of R5. right? And so that means that, that if we add W and we throw in the vectors for W and W perp, we should be able to get all of R5. So W perp is going to be a 3-dimensional subspace of R5. Okay, so what we need is for the vector x1, x2, x3, x4, x5. If I dot that with 2, 1, minus 7, 2. Oh, 2, 1. Oh, sorry. These are subspaces. Oh my gosh, I'm not seeing clearly here. These are subspaces of R4. So it's going to be a 2-dimensional subspace of R4. Okay, sorry. For some reason, when I looked at that earlier, I thought it was 5 dimensions, but it's not. It's 4. Okay, so 2, 1, minus 7, 2. Okay, so if I dot that, I need to get 0. So let's make a function out of that. So that means 2x1 plus x2 minus 7x3 plus 2x4 needs to equal 0. And I also need that when I dot x1 through x4 with this other matrix that I get 0. So this gives me 0x1 plus or minus x2 plus 3x3 plus 0x4 equals 0. So I can throw this into a matrix. Okay, and so so that is a matrix. I can do this in row echelon form by doing row 1 is row 1 plus row 2. And that gives me 2, 0, negative 4, 2, and 0. And then I'll do row 2 is equal to negative row 2. So 0, 1, minus 3, 0, 0, 0. And so I can see that I have my pivots here and here, which means I have free variables here and here. So I'll call this S and this T. And so, so I have 2x1 is equal to 4s minus 2t, and I'll have x2 is equal to 3s, and then x3 is equal to s, and x4 is equal to t. And so I end up getting that my W perp is equal to the span of the vectors. Okay, so the coefficients of the S, yeah, I can go ahead and divide all of that and make this into x1 is equal to 2s minus t. Okay, so W perp is going to be the span of 2, 3, 1, 0. That's the coefficients of the S, and then the coefficients of the T are minus 1, 0, 0, 1. And so there's my basis for W perp. Okay, next, is that matrix diagonalizable? And if so, find an invertible matrix P that diagonalizes A. So the nice thing about this matrix is that when I look at it, I can see that it is upper triangular. The lower triangle is 0. And so what that means is that my eigenvalues are sitting here along the diagonal. So lambda is 1 and then lambda is 2. And so those are my 2 eigenvalues. Now what I'm noticing here is that the eigenvalue 1 appears twice in my characteristic polynomial, and so I just need to make sure that the eigenspace is a 2-dimensional eigenspace. So let's start with lambda equal 1 and see what we can get. So if I subtract 1 from the diagonal, I'll get 0, 0, 5, 0, 0, 6, 0, 0, 1. And so that row reduces to 0, 0, 1, 0. And so what that tells me is that here is my leading 1, which means that these 2 columns are free variables. So that tells me that my free variables are, so x1 is equal to 0, x1 is equal to s, x2 is equal to t, and then this equation here tells me that x3 is equal to 0. And so the eigenspace associated with 1 is equal to the span of the vectors. I'll do the coefficients of s first, so 1, 0, 0, and then the coefficients of t next, so 0, 1, 0. So that's the eigenspace for 1. And so what this means is that it is diagonalizable because the geometric multiplicity, in other words, the dimension of the eigenspace, is equal to its algebraic multiplicity. So, so let's just go ahead and find the eigenspace here for 2. So if I subtract 2 from the diagonal, I'll get minus 1, 0, 5, 0, minus 1, 6, 0, 0, 0. And so if I row reduce that guy, I'll get 1, 0, minus 5, 0, 0, 1, minus 6, 0. And so I can see that my, leading ones are here and here, which means that this is my free variable. Oh, I'll use t, I guess. And so I get x1 is equal to 5t, x2 is equal to 6t, and x3 is equal to t. And so the eigenspace associated with 2 is going to be the span of the vector 5, 6, 1. Okay, and so, so then I can write down that it is diagonalizable, so yes, and I get that my p is equal to, I'm just going to use my eigenvectors, so 1, 0, 0, 0, 1, 0, and 5, 6, 1. And my D, my diagonal matrix, is, I'm going to use my eigenvalues, so I'll have 1, 1, 2. I just have to make sure that those correspond to the right eigenvectors and they're in the same order. And so there is my P and my D.